Hi there, this is Heath. We're looking at the second day of material on discrete dynamical systems, and let's get started. One of the things we talked about last time was that a discrete dynamical system changes the state at one time to the state of the system at a later time based on some transition matrix. That's an example of a linear dynamical, discrete dynamical system. So, for example, if x naught was, let's say, 2, 4, and my transition matrix was 1, 2, 1, 1, and this represented change per year, for example, then 1 year later, the state of my system would be 1, 2, 1, 1 times 2, 4. I apply the transition, and it transitions my input values to the output values 1 year later. And we get, this is going to be 6 and, nope, 10 and 6. Try that. Okay. One of the things that we did with one of the examples last time was we identified the long-term behavior of the system, and we can predict that sometimes based on the eigenvalues. If all of the eigenvalues have absolute value less than 1, for example, this transition matrix has 2 eigenvalues. One is 0.8 and one is 0.64. Then for any initial condition, no matter what x naught is, the limit as t goes to infinity of xt will be the limit as t goes to infinity of a to the t times x naught, which will be the limit as t goes to infinity of a to the t times some linear combination of eigenvectors This is a linear combination of eigenvectors. I don't care what x naught is, but I can represent it as a combination of eigenvectors. And then in this case, we get C1 times our first eigenvalue raised to the t power times Z naught, plus C2 times our second eigenvalue raised to the t power times Z1. Well, if we're taking the limit as t approaches infinity, this term goes to 0, and this term goes to 0, and it didn't matter what my constants were or what my eigenvectors were. This limit is going to go to the vector 0, 0. And so if all eigenvalues have an absolute value less than 1, then the long-term behavior approaches the origin. So if this was, say, a predator-prey model of some kind, then both populations in the model are heading towards extinction. That would be a sad thing, but this is just a hypothetical example. So what if all the eigenvalues are greater than 1? then following through the same logic as before, we would get to this stage here, and we would have the limit as t approaches 0 of some constant times our first eigenvalue to the t times our first eigenvector plus some constant times our second eigenvalue to the t. And this term approaches infinity, and this term also approaches infinity. And so all systems are going to be unstable. All systems are going to approach positive or negative infinity depending on what C0, C1, C2 are. So if every eigenvalue, lambda, has absolute value greater than 1, then all systems, no matter what the initial condition is, will approach an infinite vector. I'll say will approach infinite magnitude. Okay. So what if some of the eigenvalues are greater than 1 and some of them are less than 1? Then we get to the same point where we have our initial condition expressed as a combination of eigenvectors and these two terms here. And one of them is going to head towards 0. Let's let the first one go to 0, and the second one will head towards positive or negative infinity. Does that combination always add up to infinity? Not necessarily, because C2 might be 0. Whatever combination that we have might be a combination in which C1 is not 0, but C2 is 0. And so this might not go to infinity, but would go to 0 if C2 is equal to 0. And that means that the behavior of this system does depend on the initial condition. Some initial conditions will approach 0 and some will approach the origin. So in the case where we have a mixture of eigenvalues that are greater than 1 and less than 1, the long-term behavior does depend on the initial condition. It might approach 0, it might not, and it depends on the initial condition. When this happens, we say that the origin is a saddle point. I don't particularly care if you know the term at this stage, but you'll see the word saddle point again when you take multivariable, and you'll see the term again when you take differential equations. And so you'll see this in other classes as well. Okay? What we haven't talked about yet is what happens if lambda is exactly equal to 1. Now, you understand what's going to happen is that we get a term that looks like this. And 1 to the t as t goes to infinity doesn't change. And that presents some interesting possibilities, which we're going to look at on the next slide. So let's start with a definition. A Markov chain is a discrete dynamical system in which every entry of the transition matrix is non-negative, can be zero, but can't be negative, and every column adds up to 1. Let me give you an example. Let's say a courier service has 3 regions, A, B, and C, and the couriers adhere to a schedule of making all deliveries within an hour. When a driver picks up a delivery, makes a delivery, the driver picks up another package in the region where the driver is located. The couriers have determined that of the packages that originate in region A, 40% of them go to region C, 30% go to region B, and 30% of them just stay in A. They're just taken from one destination to another destination within this region. We can represent this as a column, the transformation of packages from region A. 30% go to region A, 30% go to region B, 40% go to region C. Every package has to be accounted for, and so the entries in this column add up to 1. So 100% of the packages are accounted for here. And we have similar vectors for regions B and C. In region B, 40% of the packages go to A, 20% of the packages go to region C, and 40% of the packages stay in region B. And then here's the transition matrix from region C. 50% of the packages go to region A, 30% go to region B, 20% stay in region C. We're going to aggregate these vectors into a state transition matrix. So let's answer a couple of questions based on this transition matrix. By the way, if you're looking at the PDF version of the notes, there's a typo. This should be a 0.2 and not a 0.3 because the column has to add up to 100%. Okay? So suppose the driver started in region B. So these are the deliveries that start in region B. What is the probability that the driver will be in region A after making a delivery? 40% of the packages that start in B end up in A, and so the answer is 40%. Not a hard question, I hope. The next question is a little harder, though. Suppose the driver started in region C. What is the probability that that a driver will be in region A after making exactly 2 deliveries? So we have 3 possibilities. The driver started out in C, went immediately to region A, and then stayed there for the second delivery. The driver went from region C to region B, and then from region B to region A. Or the driver stayed in region C for the first delivery, and then went straight to region A after the first delivery into the second delivery. So what are the probabilities that each of these things happen? Going from C to A happens 50% of the time. And going from A and staying in A happens 30% of the time. We're going to multiply these together. Half of 30% of the time is 15% of the time. So let's look at C to B. C to B happens 30% of the time. And then B to A happens 40% of the time. And so when we multiply them, we get 12%. And then 20% of packages stay in C, but then 50% of those packages will move to A after one delivery. So then this equals 0.10. And so if we add all these together, 15 plus 12 plus 0.10, the answer is 37%. If a driver starts in region C, there's a 37% chance that 2 deliveries later, the driver will be in region A. Can we extend this? What's the long-term behavior of the system? How does that behavior connect to the eigenvalues and eigenvectors of this system? So let me tell you some information. For this transition matrix, we have 3 eigenvalues. One is negative 0.2, one is 0.1, and the third one is 1, exactly 1. And the eigenvectors are negative 1, 0, positive 1, 1, negative 3, 2, and 7, 6, 5. And so any initial condition can be represented as a combination of these eigenvectors. As a linear combination, C1 times negative 1, 0, 1 plus C2 times 1, negative 3, 4 plus C3 times 7, 6, 5. Then the long-term behavior will be to limit as t approaches infinity of C1 times negative 0.2 to the t times negative 1, 0, 1 plus C2 times let me see if I can erase that. That erases everything. Yeah, I could do that. Times 0.1 to the t, thank you, times 1, negative 3, 4, plus C3 times 1 to the t times 7, 6, 5. This term will approach 0, this term will approach 0, and this term will approach C3 times 7, 6, 5. And what that tells us is that the long-term behavior won't be the entire linear combination. It will just be this part of the linear combination. Whatever C3 turned out to be, that part of the linear combination will be the long-term behavior of the system, which means that regardless of what C3 is, the ratio of drivers in each region will approach 7 to 6 to 5 in the long run. Okay? So let's give some definitions here. A transition matrix is said to be regular if at some point the transition matrix contains no zeros. So this is an example of a, whoops, back up. This is a regular transition matrix because it already contains no zeros. So at some time, every transition within the system has to be possible. This is not a regular transition matrix. Let's say why not. We have 3 states. From region A, 70% of the objects that were in group A stay in group A, but 30% move to group B. Of the objects in group B, 60% of them stay in group B, and 40% move back to group A. In group C, 20% of the objects move to group A, 30% of the objects move to group C, and B, I'm sorry, and then 50% stay in group C. But what's missing is that there is no way for an object that is outside group C to ever get back in. There's no arrows pointing inwards towards group C. And so some of the transitions within the system are blocked. Some of these transitions cannot happen. I cannot move from A to C, even if I were allowed to go through B to get there. It can't happen. And so it's not regular. In order for a transition matrix to be regular, every transition in the system must be possible. And it is not possible to transition from A or B into C. This is also not a regular transition matrix. There are only two states, A and B. And in every single turn, 100% of the objects in state A move to B, and 100% of the objects that were in state B to move to state A. So at any given time, all of my objects are just switching places. That's all they're doing. So why is this not regular? Because there is no time in which all four transitions are possible. This transition is never possible, and this transition is never possible. And in order to be a regular transition matrix, every transition has to be possible. And some of these transitions are not possible in this matrix. So let's look at a couple of theorems here. Theorem 4.30 says that for any Markov chain, lambda equals 1 is an eigenvalue. And 4.33 says, in fact, if the Markov chain has a regular transition matrix, then not only is lambda equals 1 an eigenvalue, but the chain will converge to a steady state that is an eigenvector associated with lambda equals 1. So in the example that we looked at with the package delivery system, what was that example, 144, we found that the steady state was a multiple of 765. That the steady state turned out to be a single eigenvector that was associated with lambda equals 1. That happens if the transition matrix is regular. If the transition matrix is not regular, weirder things can happen. Okay? Let's try another example, 146. We've got a medical researcher here studying the spread of a non-lethal virus. Ha! A virus! Imagine that! In a population of 1,000 laboratory mice. During any week, there's an 80% probability that an infected mouse will overcome the virus, and a 40% probability that a non-infected mouse will become infected. Okay, let's see what's going on here. We have two states, infected and not infected. There's an 80% probability that an infected mouse will overcome the virus, which means there's a 20% probability that an infected mouse will stay infected over the course of the week. There's a 40% probability that a non-infected mouse will contract the virus, but a 60% probability that a non-infected mouse will stay non-infected. So all four transitions are possible, and so this is regular. That's good. And our initial condition is that at time 0, 400 mice are infected, which means that 600 mice are not infected because there were 1,000 mice in the study. So that's the initial condition. What's the steady state of the virus? And we're guaranteed to have a steady state by Theorem 4.33. Anytime that the transition matrix is regular, we're guaranteed to have a steady state. Okay? The steady state occurs when lambda is equal to 1. That's the other thing that Theorem 4.33 says. So let's look at the transition matrix. For the infected mice, 20% stay infected, 80% become non-infected. And for the not infected mice, 60% stay not infected, but 40% become infected. Theorem 4.33 says that the steady state will be an eigenvector associated with lambda equals 1. But we know how to find eigenvectors associated with lambda equals 1. We're going to subtract 1 from the diagonal. 0.20 minus 1 is negative 0.80. And 0.60 minus 0.1 is negative 0.40. We're going to augment this with zeros and try to row reduce this. So if I take the top row and add it to the bottom row, I get negative 0.80, 0.40, 0, 0, 0, 0. And then if I divide by 0.8, or negative 0.8, I get 1, negative 1/2, 0, 0, 0, 0. And this says that x1 is equal to 1/2 t, and x2 is equal to t. And so my eigenvector is 1/2, 1. And so my steady state is a constant times 1/2, 1. And it has to be a constant that adds up to 1,000, or that makes this add up to 1,000. So we can solve that. 1/2 c plus 1c is equal to 1,000. And so 3/2 c equals 1,000. And so c turns out to be 666.7. And so the steady state is 666.7 times 1/2, 1, or 333.3, 666.7. The steady state will be a multiple of the eigenvector, and it will have to account for all 1,000 mice. So what this is telling us is that even though we started with 400 infected mice, over time we're going to reach a state in which only about 333 mice become infected. The initial state is worse than the long-term projection is, but there will be a long-term state in which about 1/3 of the mice at any given time are infected. All right? Have a great weekend. I'll take care.